In Lab 4 of Physics 2212, we experimented on magnetic braking with Faraday. The purpose of this lab is to collect observational data on a magnet falling through a conductive tube of aluminum foil. The interaction between the magnet and the tube is then modeled computationally. The predictions from the computational model are then compared with the observed data. The average time it took for the magnet to fall through is 0.616 seconds. The predicted time from the computational model is 0.623 seconds. Important concepts in this lab are Faraday's law, Newton's third law, and Ohm's law. Faraday's law states that a magnetic flux that changes in time creates a non-Coulomb electric field that generates voltage. Newton's third law states that opposite forces are equal. In the context of this experiment, the magnitude of the magnetic force on the loop is equal to the force on the magnet by the loop. Ohm's law relates to electrical resistance. Here are the formulas for Faraday's law, Biot-Savart law, magnetic flux, and Ohm's law. These formulas will be used to code for the computational model. In this experiment, a magnet is dropped north end first down an aluminum tube. The time it takes for the magnet to pass through the tube is then recorded 5 times and the average is calculated. The system is a magnet and the surroundings are the tube and everything else. The initial condition of the experiment has the magnet held above the tube. It is assumed that gravity and loop forces are the only acting forces on the magnet, ignoring forces like air resistance. Here are the recorded times that it takes for the magnet to pass through the tube. The average time is 0.616 seconds. The length, width, and inner radius of the tube were measured, along with the mass of the magnet and the magnetic dipole, which is from Lab 2 of Physics 2212. This information is used to code for the computational model. Here's the code for the computational model. As you can see, the dimensions of the tube and properties of the magnet are input into the code. The Biot-Savart law is also seen in line 100. After running the code, the computational model is created. The predicted time that it takes for the magnet to pass through is 0.623 seconds. This is very similar to the observed average time of 0.616 seconds. Possible errors that led to the slight difference in time include unaccounted forces, timing error, and measurement error. Air resistance and friction from contact between the tube and magnet were present when conducting the experiment, which would have altered the speed of the magnet falling. If the resistivity of the conductor were reduced as close as possible to zero, there would be a larger induced current. This would cause a larger magnetic force, increasing the force on the magnet by the loop. This would result in the magnet having less speed and requiring more time to pass through the tube. If there were holes in the tube, the induced current would decrease. This causes the magnetic force to decrease along with the force on the magnet by the loop. The magnet would then have a greater speed and would require less time to pass through the tube.